Hello everyone. After a few days of gap, I am back with a new lecture series on liquid state for your IIT-JAM in chemistry tutorial classroom. First of all, let's have a look in the curriculum. What about the subtopics in this chapter? So these are physical properties of liquid, vapor pressure, surface tension and coefficient of viscosity and the applications, effect of concentration of solutes on surface tension and viscosity, and finally the effect of temperature on viscosity of liquids. And out of this, in this tutorial number 23 of IIT-JAM chemistry and lecture number 1 of liquid state, our today's subtopics are physical properties of liquids and vapor pressure. So let's start with the physical properties of liquid. Liquids are obtained by cooling the gaseous substances below their critical temperature by applying appropriate pressure or by heating a solid to or beyond its melting point. That means if you heat up a solid substance, then it will melt into liquid, and the temperature is its definitely melting point at that corresponding pressure. And if the temperature of a gas is below its critical temperature, that is, it is in the vapor state, then on compressing it, we can also get a liquid substance. Next, liquids are more compressible and less denser than solids, but less compressible and more denser than gases. That means gaseous substances are highly compressible than liquids. On the other hand, they are very much lighter than liquids. Therefore, liquids are less compressible and more denser than gases. On the other hand, liquids are a little bit more compressible than solids, but it is lighter than solids. That means it is less denser than solids. But at this point, there is an exception, which is water. Ice is lighter than water. This is the only exception. But for other substances, this is the fact that liquids are more compressible and less denser than solids. Liquids have fixed volume but no fixed shape. We know this fact from our junior classes in the school. We know this fact that liquids have fixed volume but no fixed shape. But do you know what is the reason behind this? The liquids are having two types of energies. One is the molecular binding energy, another is the average thermal energy. That means the thermal energy. Okay. Now if you take the average of this, then we can compare this with the molecular binding energy. In case of liquids, this molecular binding energy is greater than the average thermal energy. As a result, what happens? The liquid molecules can move from one place to another, but they are not capable enough to escape from the system. There are few exceptions, that is, few molecules which happen to be the surface, they can escape, but the number is limited. And we know this phenomenon as evaporation. So let's see what is the next point behind this. The molecular binding energy is strong enough to stop the molecules from escaping. That means the molecular binding. This is the energy which is responsible responsible for the molecules from escaping from the system, unless they are not in the surface. But as I have said, that few molecules which happen to be the surface, they are a little bit capable of escaping from the surface because their energy is higher than the average thermal energy and they exceed the molecular binding energy. As a result, they can escape from the system, but not all the molecules. Okay, and this energy is not much strong to stop the molecules moving from one place to another. That means the molecular binding energy can stop the molecules from escaping, but it cannot escape the molecules. It cannot stop the molecules from moving from one place to another like the gaseous molecules. So they have a fixed volume, but they cannot have a shape. So these are the reasons behind this. Next, that is the vapor pressure of a liquid. Why does the vapor pressure develops? As just discussed, that few molecules which happen to be in the surface of the liquid, if they attain some greater energy than the average thermal energy, and if this value exceeds the molecular binding energy, then these molecules can escape from the surface of the liquid. As a result, some vapors are produced, and these vapors may have some contribution to the partial pressure to the air vapor mixture. Now let's have a look in this Maxwell-Boltzmann distribution curve, where probability is plotted against velocity of the liquid molecules at each point along x-axis. Each point, the velocity of the liquid molecules are increasing. Therefore, their kinetic energies are also increasing. Now, suppose this point where this vertical line is drawn, this point is the border line which denotes the molecular binding energy. Now the molecules which are in the left hand side of this line have lower energy than molecular binding energy, and the molecules which are to the right hand side have higher energy than the molecular binding energy. Okay, higher thermal energy than molecular binding energy. If these molecules are at the surface of the liquid and not in the bulk, then they can easily escape as vapor molecules, resulting in some vapor pressure over the surface of the liquid. This way, evaporation of a liquid takes place. Therefore, according to the Maxwell-Boltzmann distribution law, some molecules attain their thermal energies which is more than the molecular binding energy. If the molecules happen to be at the surface, then they escape into the empty space above the surface, resulting in the phenomenon known as evaporation. The next point is, if the molecules of higher thermal energy are leaving the surface of the liquid, then the total thermal energy as well as the average thermal energy of the liquid would decrease. That is why on pouring few drops of acetone or ether on the skin of your hand, you'd experience a chilled feeling there. That is, the thermal energy is absorbed from your skin. In an open space, liquid molecules continuously keep on escaping. But in a closed vessel, some of the liquid molecules revert back to the liquid surface and stick into it. That is, if you keep a glass of water without any lid, then after a few hours or a day later, you would find that the glass is dried up. This happens due to the continuous escaping of the liquid molecules into the open space. But if you keep this water within a bottle by tightly giving a cap on it, then the water level would never go down, because the vapor molecules do not have the open space to keep on escaping continuously. That is, they revert back to the surface of the liquid and stick into it. The next point is, the collection of vapor molecules in the empty space of the closed vessel attain an equilibrium with the liquid molecules at the surface. Definitely, because at equilibrium, the rate of evaporation becomes equal to the rate of condensation. And of course, it would happen within a closed vessel. The next point is, the partial pressure exerted by the vapor molecules above the liquid surface at a certain temperature and external pressure is known as the vapor pressure of the liquid at that temperature and external pressure. That is, vapor pressure of a liquid is the partial pressure of the evaporated molecules provided the temperature and the pressure do not change. Now in this context, let's get back to the previous slide where this molecular distribution picture is given, and here beyond this line, this is the shaded area which indicates the number of molecules having energy greater than the molecular binding energy, and this region is much more wider region and which is much more greater in number of the molecules which are having average thermal energy greater than the molecular binding energy. So here you find that this is the temperature which is less than this one. So T1 is less than T2. At lower temperature, this shaded area is little bit less than the shaded area of the higher temperature. The area is confined between this straight line and this orange curvature for higher temperature, and for lower temperature the area is confined between this straight line from this point to this point and the curvature. So here we find that if temperature is increased, then the numbers of the molecules having energy, kinetic energy higher than the molecular binding energy will also increase. Therefore, the point that vapor pressure increases with increasing pressure is the correct point. And the next point is vapor pressure decreases with increasing external pressure. Definitely on increasing the external pressure, more molecules revert back to the surface and stick into it, resulting in less number of vapors above the surface of the liquid. Therefore, vapor pressure decreases. As the temperature increases on heating up the liquid, simultaneously its vapor pressure also keep on increasing until it becomes equal to the atmospheric pressure. That means at a certain temperature, suppose arbitrarily if you take out of 760 torr of pressure, the vapor has the contribution of 150. Then the rest 610 torr contribution comes from the air molecules. Now if you increase the temperature, this partial vapor pressure of 150 would increase. Say it is 260. Then the rest 500 is contributed by the air molecules. This way, this partial vapor pressure gradually increases and reaches the value 760, which is the normal atmospheric pressure. And at that point, the liquid starts boiling. So at this point, bubbles of vapor start coming up from the bulk of the liquid. That is, the liquid starts boiling, and the corresponding temperature is known as the boiling point of the liquid at that particular pressure. Now, this variation of vapor pressure with temperature, how does it take place? Let's have a look. Here is the graphical presentation where vapor pressure is plotted against temperature. Here, the vapor pressure of the liquid increases on increasing temperature. This starts at the triple point of the substance and it ends at the critical temperature of the substance. Now, if we consider this line from the phase rule perspective, then you will find that this is a line which indicates a two-phase equilibrium, the liquid vapor equilibrium, where the degree of freedom is F is equal to 1. It's a monovariant system. So these are the topics which are discussed under the chapter phase rule. You will also get these lectures available in Bengali. If you want to watch these lectures, then type my name or go to my channel, Dr. Sabdurrahman Chaudhary, and then go to the playlist where you will get phase rule. But the fact is that these lectures are in Bengali. Vapor pressure of a liquid is directly proportional to temperature, and it varies as shown in the diagram, with a lower limit at the triple point and upper limit at the critical temperature. The positive slope throughout indicates that dP by dt is positive. Definitely, because this is P against T, therefore the slope must be dP dt. And this slope has a positive inclination, and this is governed by the Clapeyron equation. So now move on to the Clapeyron equation. It is obtained from the fundamental thermodynamic equation, which is dG equals to VdP minus SdT. Now if a substance is in a state 1, maybe its liquid state, and state 2 must be its vapor state. In that case, for the state 1, that is the liquid state, it is dG1 equals to V1 dP minus S1 dt, and for the state 2, that is the gaseous or vapor state, the free energy is dG2 which is equal to V2 dP minus S2 dt. And at equilibrium, that is on that point, on that line where degree of freedom is 1, these two states are at equilibrium, dg1 must be equal to dg2. That is, the right hand sides of these expressions are also equal, that is v1 dp minus s1 dt equals to v2 dp minus s2 dt. Now let's rearrange this. So dp and dt are taken as common, then dp dt has the expression s2 minus s1 equal to v2 minus v1, and definitely s2 minus s1 is delta s, and the denominator is left unchanged as v2 minus v1. And if both the numerator and denominator of the right hand side are multiplied by T temperature, then it takes the form dp dt equals to Tds minus T into v2 minus v1, where T delta S is actually involved due to vaporization of the liquid, and this is nothing but the enthalpy of vaporization. Therefore, if delta H vap, that means delta H vaporization, is the molar heat of vaporization, then T delta S can be replaced with this term delta H vaporization. So if we do so, then we get equation number 1, where V2 is the volume of the vapor while V1 is the volume of the liquid, so that this energy or this enthalpy term is nothing but the molar enthalpy of vaporization. So the terminology is here written, and equation 1 is known as the Clapeyron equation. Now move on to the Clausius-Clapeyron equation. This is a very much special case, and for a liquid vapor equilibrium, we know that the volume of the vapor phase is very much greater than that of the liquid phase. In that case, the difference may be written as only the volume of the vapor phase. In that case, the denominator take this form, T into V2 minus V1. That means T into V2 actually. V2 means volume of the vapor phase. And if this vapor behaves ideally, then it can be replaced by RT by P, and finally we get the form dP by dt equals to delta H vaporization into P divided by RT squared. And if this equation is a little bit rearranged like this, then it takes the form of equation number 2. Now equation number 2, when further rearranged, that means the pressure terms are taken in the left hand side and the temperature terms are taken in the right hand side, then we get this form, which on integration by giving limits gets the form this one, ln P2 by P1 equals to minus delta H by delta H of vaporization by R into 1 by T2 minus 1 by T1. Okay, and if this negative sign is merged within the bracket, then it takes the form delta H vaporization by R into 1 by T1 minus 1 by T2. Okay, and finally ln P2 by P1 delta H vaporization by R into 1 by T1 minus 1 by T2. This is equation number 3, and this is known as the Clausius-Clapeyron equation. So that's all for the lecture today, and now let's discuss some questions. Here, question number 1. Vapor pressure of a liquid is directly proportional to temperature, and it varies as shown in diagram, with the lower limit at A, this is the lower limit, and the upper limit at B. So identify these points. Okay, these are the options. Now we know that the lower limit is the triple point and the upper limit is the critical temperature. Therefore option A is the correct answer. Now question number 2. The vapor pressure of water at 90 degrees Celsius is 70.13 kilopascal, and the mean enthalpy of vaporization between 90 degrees Celsius and 100 degrees Celsius is 2.268 kilojoule per gram. The vapor pressure of water at 100 degrees Celsius is how many pascals? So you have to find the vapor pressure. So let's now first of all collect the data, compute the data. Here are the data which are now computed. The initial temperature T1 is 90 degrees Celsius, that is 363 Kelvin. The initial pressure P1 is 70.13 kilopascal. That means 70130 Pascal. The final temperature T2 is 100 degrees Celsius. This is the final temperature, 100 degrees Celsius. That means it is in the Kelvin scale, 373 Kelvin. And the delta H of vaporization, enthalpy of vaporization, is 2.268 kilojoule per gram. So you have to convert this into kilojoule per mole, into joule per mole. How? This kilojoule is multiplied with 1000 joule per kilojoule, and this per gram has to be multiplied with 18 gram per mole. Then kilojoule is cancelled by this kilojoule, only joule is left. Gram is cancelled by this gram inverse, and mole inverse is left. That means the unit becomes joule per mole, and the value is 40824. Thus we compute this data, and we have to now find out the value of P2. So just simply apply the Clausius-Clapeyron equation, which is ln P2 by P1 equals to delta H of vaporization by R into 1 by T1 minus 1 by T2. So just simply put these values. So in place of P2 we have to nothing to put, just we have to find out this value. But in place of P1 we have to put the value 70130 Pascal. In place of this one, in the SI unit we have to put this value 40824 joule per mole. Here 8.314, it is joule per Kelvin per mole. T1 is 363 Kelvin, T2 is 373 Kelvin. So these values are put like this, you get this way, this equation. Now the result is 40824 into, in the numerator of this portion is 373 minus 363, that is 10. So here is 10. In the denominator 8.314 is okay, and here it is 363 into 373. So 363 into 373, and the final value of this one is 0.362. So if natural log of P2 by 70130 is this one, then P2 by 70130 is e to the power this one. Okay, so this is exponential 0.362, that is e to the power 0.362, and the value of exponential 0.362 is 1.437, and hence P2 equals to 1.437 into 70130. Thus we get the value of P2 in the SI unit, that is Pascal unit, and the desired value is 1,00786. Okay, so the pressure at 100 degrees Celsius is 1,00786 Pascal. So that's all for today. Thank you and have a nice day.